There are many instances where the resistors are connected as a combination of both series and parallel. So in a circuit and even in real world, you will see the circuits has many components. Some resistors are connected in series and some are connected in parallel. If that is the case, how would you find out the effective resistance? How much power is delivered to one particular resistor? How much current is passing through one resistor? What is the potential drop across each resistor? That's what we're going to do in this video. So as an example, we have 4 resistors here, and these resistors are connected in a configuration where some resistors are connected in series and some are parallel. Let's figure this one out. So we have the 4 resistors here, R1, this is R2, R3 and R4. R1, so let's first see how does the current divide up, and how do we know that which resistors are connected in series and parallel. And remember, in series combination, the same current is passing through each resistor. Or in other words, if the same current is passing through each resistor, that means those resistors must be in series combination. So here the current is passing here. Let's call this current I. Okay, and as the current, I'm calling this current I. As the current comes to this junction here, it has now 2 paths. So one path is this way and the other path is this way. As the path has now divided up, that means, so at this point, this entire combination and this combination must be in parallel configuration. Okay, so here at this junction, the current is dividing up. That means whatever the current goes here and whatever the current comes here, so this entire unit and this unit must be in parallel combination, because in parallel combination the current divides up. Now look at here. So this combination here, this whatever the current passes through R3, the same current must pass through R4 because it does not have any other path. So whatever the current passes through R3, the same current passes through R4. That means R3 and R4 are in series combination. So first, let's find out R3 and R4 as a series combination. Okay. And in series combination, we can simply add all the resistor to find out the effective resistance. So the formula for series is, let's say I'll just write down here. In this case, we have R3 and R4. So in series combination, the formula would be R3 plus R4. And I'm calling this one not as a S, just to make it a different, I'm calling R34, which stands for the series and the combination for R3 and R4. All right. So here you see in this picture, these two resistance R3 and R4 has been replaced by one single resistance R34. So I have replaced R3 and R4 by one single resistance. So this is 20 ohm, or this is 20 ohm, and this is 40 ohm. That means these two can be replaced by 60 ohm because they are connected in series. Okay, so now I can replace these two by 60 ohm resistance. So we have 60 ohm. So again, now let's here, the current is passing here. Some current will go this way and some current will go this way. That means these two must be in parallel combination. So what's the formula for parallel combination? So the formula for calculating the parallel combination is, in this case, this is R2 and this is R34. So I'll call 1 over R234 as a 1 over R2 plus 1 over R34. Okay, so now we have to plug in the value and find out the value here. So I have done here, in fact. R234 would be 1 over R2, and this is 20, and R34 is 60. If you do the math, you'll get, I think, oh, let's see, what is the R2 value? I think R2 value is 30 ohm. It's not. This is 30 here. This is 30. Okay, so we get R234 as a 20 ohm. So that means these two resistors can be replaced by one single resistor of 20 ohm. And now we have only two resistors. So as the current is passing here, whatever the current is passing, it has only one path. The same current is passing through R1 and R234. That means these two must be in series combination. And in series combination, we just add them together. So it is 20 and this is 10. So it will be 30 ohm. Okay, so this is how we find out the effective resistance. Okay, so first thing, what you have to do, how does the current divide up? Here the current is dividing up. That means this branch and this branch must be in parallel combination. And whatever the current passes through these two, the same current passes through R3 and R4. So that means these two must be in series combination, and we have replaced by one resistance. And these two are in parallel, so I have replaced by one resistor. And these two are now in series. So we got to the final resistance, or the total resistance in the circuit, or equivalent resistance in the circuit, which is 30 ohm. And all the math is done here, 30 ohm. So we have now one voltage, 10 volt and 30 ohm. So we should be able to find out the current. And how do I find out the current here? The current would be simply equal to V over R. And what is the V here? 10 volt. What is the current here? 30 ohm. So it would be 0.33 amp. I think yes, 0.33 amp here. So I have calculated the current in the circuit here, 0.33 amp. So now let's see here. I will come back one more time. So 0.33 current is passing here. So 0.33 current is passing here. So means the current through the R1 is 0.33 here. Let me write down here. 0.33 amp is passing through this one. But this current is now dividing here into the two arms. So we know the potential drop across this one. How do we find out the potential here across this one? The potential across this one would be the current times the resistance. So let's do one step by step. And also, so here, so the current in the circuit is I, and it passes through R1, and the same current is now passing through R234. And R234 is the combination of R2 and R34. So let's find out what is the voltage drop across R234. And R234 is a combination of R2 and R34. So I think you have to understand this one. I1 is equal to I234. And what is I1 again, one more time? The I1 is the current through this one is exactly equal to the current through I234. All right. Okay. And the potential drop across R1 now, the R1 would be equal to I1 times R1, and it just found out I1 is 0.33 and R1 is 10, so it will be 3.3 volt. And the potential drop across R234, which is across this resistor, R234, would be current times the resistance. So current is I234 and R234. I234 is 0.33 and R234 is 20 ohm. So this is 20 ohm. This is 20 ohm. So if we do the math, we'll get 6.6 volt. So let's come back here one more time. So we have the potential drop. The potential drop across this one is 6.6 volt. And look at this resistor. This resistor, now we're going to backwards now. So we know the potential drop across this one. But in fact, R234 is a combination of R2 and R34. But the good thing is now we have calculated the potential drop across this one. As these two are in parallel combination, the potential drop across R2 must be equal to R34 because they are in parallel. So now we know the potential drop across this one. We know the potential drop across this one. We know the resistance value. So we should be able to find out what is the current in each ohm. Okay, so that's the trick here. First, we found out the potential difference. And now you see this resistance is made of two resistors. So the potential drop across each must be exactly the same. We know the potential difference and we know the resistance value. So we should be able to find out the current. So let's do here. So here now, okay, that's what it says. V2 here. Yes, R234 has R2 and R34 which are in parallel. So if these two are in parallel, then the potential across these two must be exactly equal, which is 6.6 volt. So once we know, then we can find out the current, and the current would be V2 divided by R2. So if you look back here, the V2 is exactly 6.6 divided by 30 ohm. I know I'm just going back and forth here. The 6.6 divided by 30 would give you this much current. The same thing, we now found out the current I34, which will be 0.11 ampere. So now, so again here we know the current through this circuit and current through this one. We know the current through this circuit here. All right. So once we know the current, and now we know now. Okay, let's come back here. R34 here. R34 is made of two resistors here, R3 and R4. And we know that how much current is passing through this one. So whatever the current is passing through this combination, the same current has to pass through R3 and R4, because these two R34 is made of two resistors, R3 and R4, and the same current must be passing through each. Okay, so I3 must be equal to I4. So that's what he said. I3 must be equal to I4, and which is already calculated 0.11 ampere. So V3 is now I3 times R3, and we calculate 2.2. And V4 is again 0.11 times 40. This is 4.4 volt. So once you know all the voltage, then we can find out the power supplied by the battery, and the power supplied by the battery is I times V, and I is the net current, the current in the circuit here, this current here. So we already have calculated this current, which is 0.33, and we know the voltage is 10 volt. So the power supplied is 3.3 watt, and this power supply is now distributed across each resistor. Okay, so there is a certain power supplied, and this power supplied, the power supplied by the battery, is distributed among each resistor. So now let's see how much power is across each resistor. How do we find out the power? We can find out the power across each resistor by equal to using this equation, I square over R. I square over R. I square times R. The power is equal to I square times R. All right. So let's come back here. Power is equal to I1 square times R1. I1 is the current in R1. And we know each value now. So if you plug in, we'll get this number here. And the same way we can find out. And if I add all these powers, we get 3.3 watt. This is exactly equal to the power supplied. So what does that mean? That means the power supplied by the battery is dissipated across all the resistor. This also means there is no storage of the power. A resistor cannot store power. All the power that is delivered to the resistor is dissipated. It is dissipated in the form of heat energy, in the form of light energy. Okay, just for example, a light bulb dissipates all the energy in the form of heat, in the form of light. Okay, so and in fact you can solve this problem using the simulation too. Let me show you quickly. So we have here, I have done exactly the same thing here. So I have 10 ohm resistor, 20 ohm, 30 ohm resistor, and 40 ohm, and exactly the same configuration. And you see now the current in the circuit is 0.33. Just we calculated here 0.33 here. So just calculated 0.33, and you should be able to calculate the current into each arm. So this 0.33 ampere is now divided into 2 arms. 0.11 goes through this one and 0.22 goes through this one. And whatever the current is passing, the same current will be passing through the 40 ohm, because these two are connected in series combination. You see here 0.11, 0.11, and 0.11 here. And now at this point, 0.22 and 0.11 ampere current adds up together, and the current in this one will be 0.33 ampere. And now you can, using the voltmeter, you can measure the potential difference across each resistor. So you can simply add one here and one add here, and this one will be negative. So the negative is because this has to be connected this way. Okay, this way, 3.3 volt. So okay, so now let's plug one here and the other here. So this one measures the potential difference across the 20 ohm. In this way, using this simulation, you should be able to find out the current and the voltage across each resistors. Okay, so and you should be also able to see the current is divided here. That means these two arms, this arm and this arm must be in parallel combination. So this is it from this chapter. Again, if you have any questions, any confusion, do not hesitate to contact me. And at the end, do not forget to like, share, and subscribe the channel. Thank you very much.